Hello, Linux Fest Northwest Virtual. In this presentation, we're going to cover an overview of the ARM assembly language instruction set and using this as an example of programming modern RISC CPUs and how they work. As we go through the presentation, we'll also compare and contrast the ARM CPU with a few other CPUs. So who am I? I'm Stephen Smith. I'm located in Gibsons, BC, Canada. I'm an author and retired computer programmer. Since retiring, I've written a couple of books which are available through APress on their website or on Amazon or any other bookseller. One is Raspberry Pi Assembly Language Programming, which is basically 32-bit ARM assembly language, and the other programming with 64-bit ARM assembly language, which of course is 64-bit assembly language for devices like iPhones, iPads, and Android devices, as well as Raspberry Pis if they run a 64-bit version of Linux, as well as the NVIDIA Jetson line of computers. So that's me, and in this presentation, we're going to be looking at ARM CPUs, which now outsell the combined weight of Intel and AMD combined. This presentation is going to look at the architecture and how it executes all its instructions, where each instruction is just 32-bit, even though it is a 64-bit processor, as we'll discuss later. And one of the cool things is that all these devices pretty well run Linux or a version of Unix anyway, even if it's, say, BSD Unix derived instead of Linux itself. So we'll look a little bit at that as we go through as well. So just one caveat as we go through, just, you know, if this was a live presentation, a lot of the things I'll say people would jump up and say, what about? That's because all rules have exceptions, but to keep the exposition simpler, I may not list all the exceptions, or I'll just mention there's quite a long list of them, and some deserve whole separate sections. Like exceptions to a strict load store architecture. So just be aware that sometimes just it's easier for me to say all or everything when there is actually quite a few exceptions. So first, just to mention, well, RISC stands for Reduced Instruction Set Computer, and CISC stands for Complex Instruction Set Computer. And the main examples of CISC tended to be older computers like IBM 360 and 370 mainframes, and that was before IBM developed their RISC line of processors, which supplanted the original IBM 360 and 370 in CPUs. But modern days, mostly when you say CISC, you think of Intel and AMD, which have very complicated instruction sets. And then RISC processors, much simpler instruction sets. So some of the characteristics is in an Intel or AMD processor, instructions are a variable length, whereas in, say, ARM running 64-bit, every instruction is 32 bits in size. And in CISC, often you can mix arithmetic and memory operations. So I could say add a register to a memory address in an instruction. You can't do that in most RISC processors. There you separate accessing memory from doing arithmetic operations. And as a consequence, RISC processors usually have a large set of registers, whereas CISC processors is usually smaller. So of course, CISC, from the name, it's larger, more complex instruction sets. And the other characteristic is CISC tends to be very variable in how long it takes instructions to execute. RISC tries for executing each instruction in one clock cycle. Now, some instructions are just too complicated, like integer division, take more than one clock cycle, just because processors aren't quite that good yet, because division is basically a subtraction loop. Now, the boundaries between these aren't as clear-cut as they used to be. Both camps steal extensively from each other and really blur the boundaries. And in fact, modern Intel and AMD processors, although they still execute their sort of legacy CISC instruction set, internally what they do is they decode the CISC instructions and then have a bank of RISC internal cores that do the actual executing. So it's almost like on the fly, they're compiling the CISC instructions into something to be executed by RISC processors. And by the same token, the RISC world's learned quite a bit for how the CISC world does things, and that sneaks in from a practicality point of view to get work done and to properly support all the operating systems and applications as they need to be supported. So why did RISC come about? And the main reason is power and heat. Where the ARM processor really took off was when Apple chose it to be inside the iPod. I mean, originally the ARM processor was developed for the next version of the BBC microcomputer. The original BBC microcomputer was based on a 6502 processor, which was very, very simple. And the people developing the next generation BBC Micro wanted something equally simple and weren't too keen on going to the complexity of an Intel processor. So they developed their own processor, and I don't think it was ever too successful until Apple came along and incorporated it in the iPod. And the reason Apple chose it was that this simple RISC processor had the performance necessary for what they wanted to do, and the battery could last for days as you listen to music. And the reason for that is the reduced instruction set. The idea is to have simpler circuitry, and simpler circuitry generates less heat and hence uses less power. And in the modern world, what's sort of been discovered as we start to reach various physical limitations on making semiconductors and chips smaller and smaller, a lot of our performance gains are from having multiple simple cores. And if you go to where the real performance is in GPUs, their cores are very simple. So as I mentioned before, even Intel and AMD use RISC cores internally. So they're really everywhere. And, you know, ARM's been around for a long time, and there's this new processor, RISC-V, which is developed out of Berkeley and is now there's various people trying to commercially implement it as a way to compete with ARM in an open source, open hardware manner. But at this point, there's not really a simple low-cost version that can run as well as ARM. But as we go through, maybe, you know, as things progress, RISC-V will take off. And it shares many of the same concepts with the ARM processors. So in this presentation, we're mostly going to talk about the ARM CPU in the 64-bit mode. We're not going to talk about, you know, although modern ARM processors will run 32-bit code, just like Intel processors running 64-bit Windows will still run 32-bit programs. ARM's the same way. But, you know, when they went from 32-bit to 64-bit, they fixed a lot of problems in their architecture and made the instruction set a lot better, a lot simpler. So we're just going to talk about their new, better 64-bit architecture and not about 32-bit, which, you know, had gone through a lot of versions and by the end was actually getting pretty complicated. So just a few key things. We got 64-bit integer arithmetic and 64-bit memory addressing. There's 4 execution privilege levels. So, you know, when you implement something like Linux, you can have user space and kernel space and interrupt space and everything else. Support for virtual memory redirection. Supports multiple cores. Even the Raspberry Pi has 4 cores. Some phones have 6 or 8. And they now have server ARM processors, which are 32-bit cores. I mean, 32 cores in each 64-bit. And there's integrated coprocessors, so it supports floating point in sizes 16, 32, and 64. 16-bit is new and only in the newest processors, but 32 and 64-bit floating point are supported in all the ARM processors if they're 64-bit. It supports SIMD, which is single instruction, multiple data, and we'll look at that later in the presentation, what that means. And there's also optional components you can get, such as cryptographic functions. Those cost money, so things like the Raspberry Pi, trying to be a $35 computer, doesn't have those. But they, you know, on phones where they need faster, secure connections. They can pay ARM Holdings to have the cryptographic function in their chips. There's, of course, multitasking support, and we'll look at some of that later on in the presentation. And often ARM CPUs are packaged on a single chip with the memory and GPU all on the same chip. So you see that in the ARM processor, in the Raspberry Pi, that the Raspberry Pi is one big chip, and then there's not much else. There's a few smaller chips, but most of all the main processing is all on the one chip that's everything bundled together under a single bit of silicon. And of course, ARM CPUs are used everywhere. They're in all Apple phones and tablets, and they're in most Android devices. Of course, Raspberry Pi, many embedded devices, servers, and workstations. And it's even rumored that the Apple Mac computer is going to switch to the ARM processor next year, so that'll be exciting. Playing with ARM assembly language, the easiest way is, of course, with a Raspberry Pi. And you can do it in 32-bit with the default Raspbian version of Linux, or you can install a 64-bit version of Linux, such as Kali or Ubuntu. There's actually a whole slew of them. Personally, I like Kali. I found that works the best, at least for what I was doing. And the various bits of hardware I had, it all just worked seamlessly. And then the good thing is, if you're playing with assembly languages, the GNU compiler collection, all the tools fully support ARM, and the GNU assembler and debugger are actually really good. And ARM Holdings itself contributes extensively to Linux, the GNU tools, and a lot of other things to make sure that their support for ARM is really good. And you can even cross-compile. So you can install the GCC tools for ARM on your Windows laptop if you want, and run them there, or on a Linux workstation running an Intel processor. So there's a lot of flexibility to cross-compile from one computer to another. That's more used in embedded devices, but some people like to, say do a big compile, say of the Linux kernel, off their Raspberry Pi, and then just copy the final result onto their Raspberry Pi. But personally, I find a lot of these single board computers actually run well enough just to do development right on the computer. And you can actually add assembly language to your Android or iOS app. Both Xcode and Android Studio both support having assembly language code in their apps. That doesn't necessarily mean Apple's App Store will like it, but they do support it in Xcode. It's not as easy or interactive as just programming on Linux on a Raspberry Pi, but it's still quite doable. Just some things about what do you have in an ARM CPU core. So this is on a single core. There's 31 64-bit integer registers. They're labeled X0 to X30, and there's a 0 register, XZR, which is whenever you read it, you'll get 0, and if you write to it, basically whatever you write to it's just thrown away. It's a no-op. There's also SP, the stack pointer, and there aren't any instructions that access both the stack pointer and 0 register both. So basically, both the XZR and SP are encoded as X31. To make the 32nd register, and just depending on context is a matter of which one is actually really accessed. Now, always doing everything as 64-bit can be a bit cumbersome. Certainly, the CPU can execute things in its arithmetic unit very quickly, but that's a lot of data to be dragging from memory into the CPU endlessly. So a lot of times you want data to be 32 bits if it doesn't need to be 64 bits. So you can actually refer to any of those registers as W0 to W30, and as well as WZR for the 32-bit 0 register. And basically that'll just access the lower 32 bits of each register. So these are, it's just a way that in a single, in an instruction, anything that you can do 64-bit, you can also do 32-bit, just how you specify the registers. There's also a program counter, and there's a status register for recording whether things are 0 or greater than, less than. Pretty standard as things that you see in CPUs. There are shadow registers for the stack pointer and the program status register. Of course, you need the program status register when you do multitasking, because if you do a multitask between any two instructions, you know, the second one could be relying on the program status counter or program status register. So this is really the only way that it gets saved. There's not another way, since the side effects on this register are nearly anything. The stack pointer is also a shadow register, because if you're in the kernel space, you want to switch to the kernel stack and not in any way rely on the user stack, which could be a complete mess or even invalid completely. So without that, you wouldn't have a very reliable operating system. And there's some other registers sometimes get shadowed as well, just to handle common cases, to save you having to push everything else onto the stack. Because with 31 registers and the register push to stack instruction can only do 2 registers at once, that's a lot of registers or a lot of instructions to push all the registers to the stack. So this helps with that for performance. All instructions are 32 bits in length. So even though this is a 64-bit processor, the 64-bit bits really means that the registers hold 64 bits and the memory addresses are 64 bits. The actual instructions are all 32 bits. And the reason is that the ARM processor wants to load these quickly and execute them quickly, each one in a clock cycle. So, you know, if the memory controller can load 64 bits from memory at once, it can actually load 2 instructions. So that can help keep the pipeline full. And basically, since there's 32 integer registers, that means it takes 5 bits to encode each register. And instructions are usually of the format, you know, do something like add destination register and the 2 source registers. So a lot of instructions require 3 registers, so that's 15 bits gone right there. And this all limits the number of bits that can be used from the opcode, hence the reduced number of instructions. And ahead we'll look at some other tricks they use to lower the number of operands required. And as a result of this is that immediate data is far smaller than the register size. So immediate data is when you say do load, a register with a constant like, say, the integer 5. So in an Intel processor, you can actually load any 32-bit quantity in using immediate operands. In the ARM, often the size of the immediate data is like 6 bits, which is very small. So you can't use immediate data for a lot of things. And if we look at here, we have the format of a typical instruction. The first bits actually means are the registers which are on the right side 32-bit or 64-bit registers. So is this a 32-bit or 64? Like, is that the size of the data? So that really means is like for RM, is that like a W register or an X register? The opcode is sort of split in 2 places, but it's basically ultimately 6 bits of what the opera code is. And set condition code is all the instructions. A lot of the instructions, you can either set the condition codes in the status register or not, depending on if this bit is set. Shift for a lot of instructions is a hard-coded shift of the immediate operand, or so that you can get a bit more flexibility out of that. And we'll look at that in the next instruction or so, in the next slide or so, of what you do with these 4 shift bits. And basically they're going to correspond to shifting the immediate operand. In 32-bit ARM, the shift was much bigger, and typically the immediate was 8 bits, so it was a byte, and then shift would let you put that byte in any position in the register. But with 64-bit, there's not quite as many bits since there's more registers. So it's a bit more limited in what you can do, but we'll see what you can do in a sec, or a couple slides on. Next up, we have tricks with the 0 register. So this is a trick that the ARM processor and the RISC-V processor use extensively to limit the number of opcodes. So for instance, move the immediate value 3 into the register X3 is not an actual instruction, but it's an alias for OR X3 with the 0 register and 3. So an OR of 0 and 3 is 3, and then the result goes in X3. So that's how a lot of instructions are implemented using the 0 register. Now, the disadvantage of this, of course, is that if you didn't have to specify the 0 register as one of the registers, the immediate constant could be 5 bits bigger. But the ARM designers felt it was more important to save on the opcodes. And I think studies by both ARM and RISC-V has found this is the more efficient way to do things. And for instance, comparing X3 to the immediate value 3 is actually an alias for sub, and then S means set the status bits of XZR, so that basically says the destination or the result is thrown away, but it'll set the status bits based on subtracting 3 from X3. Clever use of the 0 register removes the need for many opcodes, and it saves a few bits, which is really important when you only have 32 bits for your instructions. And then the aliases are in the assembler, so they keep your assembly language program more human readable. So what we're going to do now is, okay, you've got these 32-bit instructions, but how the heck do you actually get a 64-bit register loaded with 64 bits of data? Now you could say, well, you load it from memory, but then the problem is how do you get the 64-bit memory address into the register to redirect it to load the data? So there's a number of tricks that are used in the ARM processor, and RISC-V is pretty similar. So the largest immediate operand is 64 bits, and it's really, I'm sorry, not 64, 16 bits. And most of them are a lot smaller, like the 6-bit example we saw before. So there's a painful but guaranteed way of loading 64 bits of data into a register, and basically use 4 instructions, each one loading 16 bits. And to do this, we use that shift operation those shift bits in the instruction we mentioned before. So for instance, to load X2 with this horrible 64-bit value, we go move X2 with the first one, then move K, which means move keep, in that it won't affect the other bits besides the other 48 bits except for the 16 that we're affecting. So we basically do 4 instructions. So to load 4 times 16 bits in. So we load the low order 16 bits, then the next 16 bits shifted over 16, the next 16 bits shifted over 32, and the next 16 bits shifted over 48. And this move isn't the same move as I mentioned before. This is actually an alias of another instruction, which the reason that it's not move, it could be move K because we actually fill in all 64 bits, but usually when we do this, we do the first one as move because it'll zero the other bits. The instruction aliases too. Another way to load 64 bits into a register is relative to a register that already has a value that we want. So a lot of times you want a memory address, and what you can do is add an offset to the stack pointer or the program counter. So here we want to load that same horrible value that we did in the last slide. So if we did that in the instruction, which is like load register X1 with that horrible value, which obviously can't be encoded into the instruction in 32 bits. But what the assembler does is it rips apart the instruction, and if you look at disassembling the programs generated, you'll see it does something like load register X3, 8. And what this means is it's going to load X1 with whatever is pointed to by the program counter plus 8 bytes. So the program counter is pointing at the next instruction, and then we add 8 bytes to it, and we get .quad, which is a memory that it's actually stuck into the code. So it actually will stick it at the end of the routine. It won't stick it in the middle, but Basically, the assembler will translate these things into using a PC relative address and a bit of memory stuck into the code section of your program. The same way, if you want to load an address, you'll see load register x1 with the address of hello world, where hello world somewhere is, say, defined to be a string. And basically, this works the same way. It'll end up being a PC relative instruction. Just one other note about that is what it will actually do is hello world can be in the data segment. If it's in the data segment, then in the code segment, it'll put the address of where the data is in the data segment in the code segment and do an indirection. So that works fine as well. So how to load a 64-bit register, part 3. So the load register relative to the program counter has a range of plus and minus 1 megabyte. Part of the reason is that it has to be 32-bit aligned, so it's actually, when you give the offset, it's in words and not bytes. There's also a similar load instruction, ADP, but it loads measured in pages. So pages of 4K, and basically using the page one, you can get a plus or minus offset of plus or minus 4 gigabytes. And the C compiler uses this to load the start of its data segment, and then it can access the elements in the data segment using offsets from this base register. So basically, in a routine, it'll first load X, say for instance, X0 with the address of its data, the start page of its data segment. So this will be the program counter, the page the program counter is in plus this value times 4K. And then it accesses it knowing, say, X0 and then 56. So this is an indexed addressing mode where basically it's going to do an indirection from X0 plus 56. So that's another way that you can get at the data. The ARM processor is a load store architecture, so that means you typically do these load registers to load your data into registers, and then you do arithmetic operations on them, and then you store them. So we see load register X2 with whatever's the address, whatever's stored at the address that's in X1. So the square brackets meaning to do the indirection. And then load register X3 with whatever is stored in X1 plus 8. And then we do the addition, so X4 equals X2 plus X3, and then we store X4 back into whatever X1's pointing to. So this is very efficient. It can execute those instructions very quickly. And basically the adder is free, so the second load, of course, does an addition of X3 plus 8, or sorry, the X1 plus 8, but it can do that because it's not doing, say, another sort of operation. So, in the second instruction, it can use the adder since nothing else is using it. The only problem with this is synchronization, so we'll talk about that next. And basically, if we have two cores executing the same code, say you want to set a spin lock like you do in the Linux kernel very often, you basically, you load say X1's pointing to your spin lock, you load it into X0, you compare, is it 0? If it's not 0, you wait for the process who's got it to finish, and then you set it to 1 and store it. The difficulty being that if the spin lock is available, both these things execute exactly the same. They'll both get it because they both read 0, and then they both store 1, and nothing knows that they both got the same thing, and then they'll corrupt the Linux kernel data structure that's protected by the spin lock. So that's a bad thing. So any RISC processor has to somehow either extend load store or provide another operation. So you can either lock the memory or do the increment atomically. So the RISC-V likes doing things atomically. The ARM processor prefers locking the memory location. So So if you do it atomically, then you basically have an instruction, say, that can do an increment of a memory location. So you're sort of breaking load store by the architecture by combining, doing that operation. Load acquire, store, release is what ARM does. So it still looks load store, but you are having, some information saved across a bunch of instructions. So we can actually see this in the Linux kernel source code. So for instance, under the Linux kernel, Arch is where all the architectural specific stuff for the different processors source code is in the Linux kernel source code. ARM64, of course, is what we're looking at. Then include ASM. And then one example is this atomic LLSC.h contains this decrement if positive routine. Now, assembly code in the Linux kernel can be very confusing because nearly everything is done as macros, which means all the registers are passed in as parameters and often instructions are passed in as parameters. But if you just think that, these percent things are just particular registers, then it's easy enough to follow along the code. So what happens is LDXR loads the register, but it's setting an acquired that we're acquiring this memory address and to monitor it. Then in this case, it wants to decrement if it's positive, so it subtracts 1, and then it branches out if it's gone negative because it wasn't positive to start with. So that's just what the routine wants to do. And if it's successful, then it does the STL-XR. Now, basically what this routine will do is it'll either succeed if nothing else is written to that memory address, or it'll fail by setting the zero or clearing the 0 flag, and then the CBNZ will jump to and I guess this is just a way in assembler, the 1B means go to the number 1 back. And you do that in macro, so you don't get multiply defined symbols. It's just the trick to how you can put labels on instructions without getting them multiply defined. So there's similar routines in futex.h, which actually has a lot more of them. They're just a bit more confusing to read because typically the instructions are passed into the macro as well. And this is optimistic concurrency, in that the memory is not blocked to read. It's only when it goes to save that it's been monitoring the memory, and if someone else wrote to it, then your STL-XR will fail and you'll have to do it over again. So this works fine, and you'll see it in these 2 kernel files for doing the kernel spin locks that protect all the Linux kernel data structures. And just, there's ARM implementation limitations on using this mechanism. Certainly the cheaper ARM processors can only have one of these going at once in an individual core, so you can't do a bunch of LDXRs on different memory addresses. You have to sort of do the LDXR and the STL-XR together. The way we've done it here. You can't get too fancy because it's expensive for the core to keep track of this memory address and then monitor what's happening to it. So you basically get one address per core. Then there's the arithmetic logic unit, the ALU, and it does all your basic arithmetic things like addition and multiplication. There's quite a few multiply add instructions. So these are where, x equals, a times b plus, some sort of running total. So very useful instructions for doing things like matrix multiplications and dot products and those sort of things that you see an awful lot now in graphics and artificial intelligence. Of course, has comparisons, logical operators, and bitwise operators. So everything you'd expect in a modern CPU. Quite a full set of instructions. But again, they're careful to make sure each instruction is needed. And you'll find a lot of the instructions are actually aliases. So I listed multiply as an instruction here, but it actually isn't. It's an alias because, of course, multiply add does multiply as part of it, so it can add the 0 register, and there you get the multiply. So, by using the 0 register, there's actually a smaller set of instructions than I've listed here. Memory accessing modes, basically, of course, if you have a memory address in the register X1, you can load what's pointed to by that memory address into a register, as you would expect. And then we have pre-indexing, where you can add a number to that. So like X1, 8, a lot of times you might use that as an offset into a structure. And if you do it in a loop, if you put an exclamation mark after it, then it will also save X1 as X1 equals 8 afterwards. And then the other case is post-indexing, where what it will do in this one is it'll load from X1 and afterwards add the 8. And there's no exclamation mark because since it's adding the 8 afterwards, it doesn't make any sense to specify this unless you want it saved. So the ARM processor's got some good indexing modes, which actually make doing sort of for-type loops very simple and very efficient. Just to talk a little bit about the coprocessors, there's the floating point unit, which does floating point operations, and there's the Neon SIMD processor, which we'll talk about on the next slide. So just to talk a little bit first about the floating point unit, basically there's 32 128-bit registers, which is shared by both processors. So the floating point unit can't do 128-bit floating point. It just does 64-bit, 32-bit, or 16-bit. So when you're dealing with the floating point register, basically you refer to the registers as D for 64-bit, S for 32-bit, H for 16-bit. And so in the example below, we see that we're loading the pair of registers S2 and S3 from what's pointed to by X0, and then doing a floating point subtraction, S4 equals S2 minus S0. So that's how we do floating point. And because we're doing, we said the registers are S registers, that means they're 32 bits, which means that basically, even though register 2 is 128 bits, in this context, we're only using the bottom 32 bits of it. So you might say, okay, well, what are all those bits for? And that gets us to single instruction, multiple data, or the Neon processor. So what the Neon processor does is it breaks these 128-bit registers up into lanes. So that means that a single 128-bit register could contain 2 64-bit registers, 4 32-bit values, 8 16-bit values, or 16-byte values. And basically what the single SIMD means is single instruction, multiple data. So a single instruction is going to operate on multiple bits of data at once. And basically what it does is it breaks the register into lanes, and then it operates on all the lanes simultaneously. So in the little bottom diagram of this picture, we have lane 1, 2, 3, and 4. And we're looking at registers V0, V1, and V2. And so V0 and V1 we're going to add together, and this is what's contained in the lanes of each one. We then execute the instruction add, and then V2.4S, so basically it just means register 2, and then it's split into 4 single precision floating point values, is going to be the sum of registers V0 and V1 split into 4 32-bit values. So basically it adds each one of these lanes independently, and we get 4 floating point additions done at once. So that's what the Neon processor does. And this is very similar to Intel's AVX processor. So Intel basically, when they, after the Core 2 Duo, when they started doing the core architecture for i3, i5, i7, introduced their AVX instructions, which are very similar to the Neon. Inside the Intel processor, there's a bunch of bigger registers. Depending on the generation of Intel processors, they started at 128 bits, then extended to 256, and are in the process of the newest, best server chips that are just coming out do 512 bits. So right now, the ARM processors just do 128 bits, and I don't know if they'll extend it or not. But anyway, it can be a very efficient way of doing processing. So then there's libraries from ARM and from different other people, where you get some very good algorithms implemented in Neon. So you can either do it yourself in assembler, or you can use one of these other libraries. If you have a look at ARM's website, they have a couple of very good ones for doing common things like matrix multiplications and Fourier transforms, all those sorts of things. So Linux itself actually uses the Neon coprocessor for encryption. So for instance, under Arch ARM64 crypto AES_neon.s, and you look in there, so this is just a part of the routine just to see that within the Linux kernel itself, people have implemented, whether it was ARM engineers or volunteers, implemented a lot of the cryptographic routines using the Neon coprocessor. So this is just one of the many macros in the Linux kernel under this section. So I won't go into too much detail, just to show that you can see that you're doing it, that the Neon is used, and it is actually used by the Linux kernel, which is, I find, interesting. And this one's actually using, you know, because it's doing encryption, is actually looking at, you know, for instance, the first one, v9.16b. So it's actually split the 128-bit register into 16 bytes. So it's actually doing 16 operations at once. The TBL and TBX for doing table lookups, which is handy, and then subtracting. So this is part of the AES cryptographic algorithm. And if you look in the source code for the Linux kernel, you can actually find the whole routine all implemented in the Neon processor. And if that's confusing, you can always look at one of the other implementations. But I find that you know, the Linux kernel really takes advantage of everything that the ARM has to offer. And that's why the implementation and the performance of these cheap little computers like the $35 Raspberry Pi, or, you know, some of the burner Android phones, is so good. So that's my presentation. It's a very fast overview of the ARM CPU and what it can do, and some of the aspects that you consider when you do assembly language programming. If you have any questions, you can email me at my email address. Have a look at my blog, smist08wordpress.com. I'm on Twitter at smist08. If you're wondering what smist08 is, because I'm Stephen Smith, it's impossible to get my name on anything on the internet. So everything I go to, Stephen Smith, is already taken. So smist08 was my employee ID when I worked at Computer Associates, and then that continued on when when ACPAC International got formed, and then it got bought by Sage. So that stayed as my employee address, my employee ID throughout most of my career. So I remember it, and it's easy to get on all these things. So that's why I use that still for internet type things. And check out my books. Like I said, they're on Amazon. You can also find them on Apress's website, Raspberry Pi Assembly Language Programming, and Programming with 64-bit ARM Assembly Language, if you want to learn more. So thank you very much, and have a great continuing virtual conference, as well as have a great summer, and hopefully life gets back to normal and we can all meet in person again next year. Thank you.